In this video, we're going to introduce some of the fundamental concepts associated with probability. So we're going to start with talking about an experiment and a sample space. So probabilities are assigned to the possible outcomes of an experiment, and they represent the likelihood of occurrence for each outcome. So when we use the term experiment, you might be picturing something like a chemistry lab. Experiment doesn't have to mean something that you perform in a lab. So when we think about an experiment within the context of a probability problem, we're thinking about an action or a sequence of actions that has a specifically defined set of outcomes. So think of performing some type of action where you can officially determine these are the possible outcomes that could result from this action or this series of actions. That's what we're going to think of as an experiment. So the set of all possible outcomes, not necessarily which one is going to happen each time, but just think of it as all the possible ways the experiment could go. That's what we're going to call the sample space, and we're going to label that with a capital S. So it is a set. We know sets are labeled with capital letters. We're going to label this specifically with a capital S. Now, any subset of the sample space is called an event, and we're going to label that with a capital E. We can label it with different labels, but in general, E for event. So think of an event as just being one particular outcome or maybe a combination of outcomes. So if the sample space is all the possible outcomes, an event is some specific set of outcomes that we're interested in within the sample space. So if E contains only one element, in other words, it's referring to one specific outcome in the sample space, then we'll call it a simple event. And if E contains more than one element, then we're calling it a compound event. So let's start by just talking about how we define the sample space, how we analyze an experiment, and then we'll look at some actual probabilities. So for example, a nickel and a dime are tossed. How do we define a sample space for this experiment under each of the following conditions? So you're going to find that defining the sample space depends on what we're interested in. So when we run an experiment, so for instance, here the experiment is actually flipping the nickel, flipping the dime. That's the physical sequence of actions we're taking. So that's what we're going to think of as the experiment. The sample space is going to depend on what we're actually interested in terms of outcomes. So maybe we're interested in something numeric, maybe we're not. You're going to find, though, that for each experiment, you can often define different sample spaces just depending on what kind of outcomes you're interested in from your experiment. So we flip a nickel, we flip a dime. Maybe, for instance, we're interested in whether each coin falls heads or tails. That's going to determine how we define the sample space. So the sample space is just all the different outcomes we can get from our experiment based on the fact that we're interested in whether or not we get heads or tails for each flip. So when we define the sample space, what we're doing is we're determining what are all the different outcomes we get from the experiment, and then let's make a list of them. So we're going to label it with capital S for sample space. Now we're interested in whether each coin falls on heads or if it falls on tails. So we have to think about all the different ways we could get an outcome for flipping a nickel and flipping a dime. Well, one possibility is that we flip them and both land on heads. So we could label that as HH for two heads. Another possibility is maybe we get heads and tails. So maybe heads for the nickel and then tails for the dime. Another possibility is tails and heads. So that would be tails for the nickel and heads for the dime. Notice these are not necessarily the same outcome because the heads results for one coin and the tails result for another. There's also the possibility that we get two tails, which would be tails for each of the coins flipped. Now keep in mind, these are the only outcomes we can get. There's no other combination from this particular experiment. So that's going to be the entire experiment sample space. So in this case, the sample space has 4 elements. Defining the sample space is important, but it's also important that we be able to count how many elements are in the sample space. That's going to be one of the key components of probability, is how many elements are in the sample space. Now, what if we perform the same experiment but we're interested in something different? So suppose we're interested in the total number of heads that appear in a single toss of the 2 coins. So we're running the same experiment, but now instead of being interested in just heads, tails, what are we actually getting in terms of the combination of those 2 coins? Now we're specifically interested in the total number of heads that we get when we toss the 2 coins. Well, in that case, we have to then think about what are all the different possible numbers of heads that we could get when we flip the 2 coins. We can actually use the previous sample space to help us think about this. So one possible outcome is getting 2 heads. So that would result in 2 for this particular sample space as defined, where we're interested in the number of heads. If we were to get heads, tails, or tails, heads, notice that's going to be 1 head for each of those outcomes. So another possible outcome in this sample space would be 1, representative 1 head. And then the other possibility is flipping and getting 2 tails. And again, if we're interested in the number of heads, then that just means that outcome would be represented as 0. So this would be an equally accurate sample space representative of this experiment. It just represents a different kind of outcome that we're interested in just based on how that's being defined. So both of these sample spaces would be considered reasonable sample spaces for this experiment. The one we're interested in just depends on the situation we're in and what we're trying to do. Now let's look at another one. So consider an experiment of rolling 2 dice. We want to define the sample space for all the different combinations, and then we're going to use the sample space to define some events. So we're going to take it a step further. So I've tried to organize this in a table format, particularly when we're talking about doing 2 steps. We did 2 steps for this particular experiment where we flipped 2 coins, but it was fairly straightforward to define all the different possible combinations for outcomes. When we have something like dice, there's 6 outcomes for each die being rolled. So die is going to be the singular of dice. So defining a sample space in this case means we have to be a little bit more organized. So we can potentially define the outcomes as ordered pairs, where each element in the ordered pair is just going to tell us the number on each individual die. So along each row, I've defined whatever number we had in terms of the dots on the first die, and then the next one, the next element in there, defines the number of dots for the die in the column. So 1, 1 would be 1 for the first die and 1 for the second. 1, 2 would be 1 for the first die and then 2 for the second, and then so on and so forth for all the combinations, all the way up to 6, 6. Now notice if you organize them in this manner, then you can actually determine sort of how values are increasing. Because one thing we're typically interested in when we're looking at rolling a pair of dice, is what's the sum of the dots. Those are going to be events that we typically like to define. What kind of sums do we get if we sum up the dots on the dice? If you organize the sample space in this kind of way, rather than just making a list like we did for the 2 coins, it's going to be easy to spot all the different combinations that sum to the same value. So for instance, if you were to sum up the 2 dots for this particular pair, 1 plus 1 is going to be 2. Now notice what comes on the next diagonal. That would be 1 and 2, and then 2 and 1. So both of those outcomes, 2 plus 1 is going to be 3, 1 plus 2 is also going to be 3. And then the next diagonal is going to be 3 plus 1, 2 plus 2, and 1 plus 3, all of which are 4. So organizing the sample space in this manner is going to organize specific outcomes in a specific way, so it's easy to analyze what we're looking at in this particular situation. So let's use this sample space and let's take it one step further. So we want to define all these specific events just based on how they're described. What that means is we want to make a list of all the elements that are in the sample space that are representative of this particular event. So for instance, event 1 is that a sum of 7 turns up. So what we want to determine is what elements in the sample space, what possible outcomes in the sample space represent getting a sum of 7. We have to keep in mind that there's potentially more than one way to get a sum of 7. So every possible outcome in the sample space that represents getting a sum of 7 would be included in this event. Well, let's go back to the sample space. So we're interested in a sum of 7. Well, one way we can get a sum of 7 is going to be 6 and 1. So 6 for the first die and then 1 for the second. We could also get 1 and 6, so it would be the same combination but flipped. Maybe one die is one color, one is the other color, and so we have a distinct relationship between which one is which. Now we could get 5 and 2 and 2 and 5, and the other possibility would be 4 and 3 and 3 and 4. So notice that's going to be on the longest diagonal, and specifically there's 1, 2, 3, 4, 5, 6 different ways to get a sum of 7. So this event, this subset of the sample space, is all the different combinations, in this case all 6 of them, that result in us getting a sum of 7. Now what about a sum of 11? Well, let's go back to the sample space. Think about all the different ways you could get a sum of 11. Well, one possibility is we roll a 6 and a 5, or we roll a 5 and a 6. So same combination, but the dice have flipped. Those would be the only 2 ways we can roll exactly an 11. So those would be the 2 elements in this particular event. So that would be our subset of the sample space. Now maybe instead of a specific sum, we're interested in a sum that's greater than a certain amount or less than a certain amount. So how about a sum of less than 4? Well, that could be a sum of 1. Is that possible? Can we roll a 1? Well, we're rolling 2 dice. So remember, we can't actually roll a 1. The lowest number we can get is 2. So we could roll a 2, or maybe we could roll a 3. So go back and reference the sample space if you need, or maybe you can think about this mentally in terms of what outcomes are going to represent elements in this particular event. So rolling a 2, the only way to get a 2 is going to be 1 and a 1. Now there's 2 ways to roll a 3. So we could get a 2 and a 1, or we could get a 1 and a 2. Those are the only ways to roll what we're interested in. So in those cases, those are going to be the particular outcomes in this event. So that's going to be all 3 representative of a sum less than 4. And then last but not least, a sum of 12 turns up. Well, there's only one way to roll a 12. 12 is the highest sum we can get. The only possible combination that results in rolling a sum of 12 is going to be 6 on both dice. So one element in this particular event, so this would be considered a simple event. So this is a simple event because only one outcome is in this particular event, only one element in this subset of the sample space. All of the other events would be considered compound events because there are multiple outcomes represented in each of those events. So we know what a sample space is. We now know what an event is. We're going to look at these in more detail. I want you to think of the experiment and the sample space as where you start with any probability problem. So you're defining the actual action or sequence of actions that you're taking, and you also have to have a sense of what are the different outcomes. So once you perform this outcome, or once you perform this experiment, what are the different outcomes you can get? Not only are we interested in the outcomes themselves, but we're also interested in how many possible outcomes there are. So counting, all those things we talked about with respect to counting, all of that's going to come back. We have to be able to count how many ways we can get outcomes, either outcomes on the whole for the whole experiment, or specific outcomes maybe representative of a particular event. So let's define probability. So probability can be expressed in one of 2 ways, either as a percent from 0% to 100%, or as a fraction or decimal from 0 to 1. So an event that is certain to occur, it's guaranteed to occur, is assigned a probability of 1 or 100%. In other words, it's 100% likely that this event will occur. Events that are very likely to occur will have probabilities that are close to this value. So higher values, values that are closer to 100%, or for our purposes, we're going to use fractions and decimals, values that are close to 1 are considered to be representative of events that have a high probability. Now, an event that will never occur, in other words, it's impossible that the event can occur, that's going to be assigned a probability of 0 or 0%. So events that are unlikely, that are not likely to occur, are going to have probabilities close to 0. So the higher the number is, the closer it is to 1, the more likely it is to happen. The closer it is to 0, the less likely it is to happen. And one thing we're going to find is that the sum of the probabilities of all possible events in the sample space, in other words, if you were to look at the whole set of outcomes, remember we defined what a sample space is. Think of this as your sample space, this is your sample space, this is your sample space. If we were to look at every single individual event in the sample space and define the probability for every individual outcome, and then take the sum of all those probabilities, that sum is always going to add up to exactly 1. So that's going to help us make sure, among other things, that we define probabilities correctly. If you were going to actually take the probability of every single outcome in that sample space, once you add up all those probabilities, they should always add up to 1. The tendency is to rate them too high so that the probabilities add up to more than 1. If that's the case, then you know that number 1, maybe you just added incorrectly, but more than likely it means that you probably determined your probabilities incorrectly and you've assigned probabilities that are too high. So there's 2 different versions of probability. There's what we call theoretical probability, and then there's what we call empirical probability. So theoretical probability in most cases applies when all possible outcomes are equally likely. We're going to think of theoretical probability as the probability we use when we're just analyzing an experiment from the outside. So we're not actually physically performing the action that the experiment requires, but based on our understanding of the experiment, we're defining all the different outcomes, and we're just using logic to determine how likely one outcome is versus another. Now, we do have a formula for probability, and we're going to fall back on this formula every time. So we're determining the probability of an event. In other words, how likely is this one particular outcome or this particular combination of outcomes versus the other outcomes in our sample space. And that's what we're going to think of as the probability. So we have an event E. So we're going to assume E has N of E equally likely outcomes. In other words, this is going to be the number of elements in the event E. How many different outcomes represent in us getting event E? So based on the events we have defined above, if this particular event has an element size of 1, N of E would be 1 in this case because there's one outcome representative of this event, whereas the first event has 6 outcomes representative of that, so N of E in this case would be 6. So we define our event and we know how many outcomes represent that event. And in this case, in theoretical terms, we're thinking about equally likely outcomes. In other words, in this particular event, any one of these outcomes is just as likely as any other. We're just as likely to roll one of these combos as we are any other. So that's what equally likely means in this case. So our event has a certain number of outcomes, and the sample space has N of S equally likely outcomes. Think of that as the total number of elements in the sample space. How many different unique combinations are there? How many different outcomes are there in the sample space? That's going to be N of S. Then the probability of our event, of our specific event we're interested in, is going to be N of E divided by N of S. Now, rather than memorizing a formula, I want you to think about what this represents. What does the numerator mean? What does the denominator mean? So the numerator represents the number of outcomes in the event. In other words, how many different ways are there to get a particular combination of circumstances so that we fall under this event? How many ways are there to roll a specific sum? How many ways are there to draw a card that looks a particular way? That's always going to be our numerator. It's going to be the number of outcomes in the sample space that represent the particular event we're interested in. And then the denominator is always going to be the total number of possible outcomes for the experiment. In other words, if we just look at the experiment as a whole, how many different unique outcomes are there? That's going to be the denominator of our probability. So we're going to define that fraction, and that fraction is going to represent our probability. Now we know with fractions they need to be reduced. We will need to reduce the fractions. If instead of a fraction we want a decimal, all we have to do is take that fraction and treat it as an actual division, and we just divide numerator divided by denominator, and that's going to give us the decimal version of our probability. Okay, so let's look at a few examples. So consider the nickel and dime example and the sample space we defined based on the combination of head and tails. So specifically we're looking at, did we get a head for our nickel, did we get a head for our dime, and so on and so forth. We want to determine the probability assignment, assuming the coins are fair and balanced, then use it to find the probability of each of the given events. Okay. So let's rewrite the sample space. So if we're interested in the combination of heads and tails, we determined that the possibilities were 2 heads, We could get a head and a tail, we could get a tail and a head, and then we could get two tails. These are the only possible outcomes when we flip those two coins. Now first, what is the probability of getting one head and, in other words, one tail? Okay, so anytime we look at a probability question, we're asking ourselves about the numerator, we're asking ourselves about the denominator. So let's start with the denominator. Think about the experiment. What is the experiment? Well, the experiment is flipping the nickel and dime at the same time. Okay, so based on the experiment, what's the sample space? Well, our sample space is all the different combinations we can get. When we're defining the denominator in our probability, the denominator is always going to be the number of elements in the sample space. In other words, it answers the question, when I run my particular experiment, how many different outcomes are possible in total? Well, based on this particular experiment, there are 4 unique possible outcomes. So that means the denominator of our probability is going to be 4. Now, 9 times out of 10, the numerator is going to be the more challenging component to determine. So what does the numerator represent? Well, the numerator represents the number of possible outcomes in the sample space representative of the particular event, the particular outcome we're interested in. So what we're interested in is getting some combination that represents one head and then, of course, one tail. Well, we then have to ask ourselves, going back to the sample space, how many ways are there to get one head and one tail? Well, we know we could get a head for the nickel and then a tail for the dime, or we could get a tail for the nickel and then a head for the dime. Those are the only possible ways we can get one head and one tail. So that means there are 2 different ways to get this particular outcome in question. So the numerator of our probability is going to be 2. So the total number of outcomes represented in the event, that's going to be 2. And the total number of outcomes in the sample space, that's going to be 4. Now, anytime you define a probability, remember it's going to be no greater than 1. So your numerator should always be no greater than your denominator. You could have something like 4 over 4, but you couldn't have something like 5 over 4 because that's going to be greater than 1. In most cases, the numerator is going to be strictly smaller than the denominator. So that's a good check in terms of making sure whether your answer makes sense. Numerator should be smaller than denominator in general. And then, of course, we need to reduce that. So 2 over 4, they have a common factor of 2. I can divide that out, and it reduces to 1/2. And then if we want that as a decimal, we just divide. So 1 divided by 2 is going to give us 0.5. So either of these would be considered correct probabilities for this event. Now, what about another event? So what's the probability of getting at least one head? Well, what's the difference? The first event is getting exactly one head and then one tail. Here we've added the phrase at least, so we're interested in getting at least one head. Now, the probability is always structured the same way. So the denominator is the total number of outcomes in the sample space. How many different total outcomes are there for the experiment? Well, we know there are going to be 4, so our denominator is going to be 4. And then the numerator is all the different ways we could get at least one head in our sample space. Well, what does that mean in terms of at least? Well, it means we could get one head, or potentially we could get 2, just based on how our experiment is defined. Well, how many different ways are there to get at least one head? Well, we could get heads, heads, that is at least one head. We could get heads, tails, or we could get tails, heads. Tails, tails would not fit into this event because it doesn't represent getting at least one head. So we would have all of these outcomes in the sample space except for tail, tails. So how many different ways are there to get at least one head? Well, in this case, there's 3 different ways. So our probability is going to be 3 out of 4, or 0.75. Okay, what is the probability of getting at least one head or at least one tail? Okay, well, this is kind of 2 things in one. At least one head, well, there's 3 different ways to get at least one head, but it also says, okay, it's all right if we get at least one tail. Well, that would be heads, tails, tails, heads, and tails, tails. So if you follow everything we counted, that's going to be all the elements in the sample space. So how many ways are there to get at least one head or at least one tail? Well, each outcome in the sample space represents at least one head or at least one tail. So there's 4 different ways to get at least one head or at least one tail, divided by the total number of elements in the sample space, which is 4. Now, any number divided by itself is going to be 1. So this particular event, as described, has a probability of 1. What that means is that it's guaranteed. It means there's no way that you get an outcome that doesn't fall under this event as described. Anytime you perform the experiment, you're going to get at least one head or at least one tail. So this particular event is guaranteed to occur anytime you run the experiment. That's what it means when we assign a probability of 1 or 100%. It means it's guaranteed to happen. Now, what's the probability of getting 3 heads? Well, think about it. We're flipping a nickel, we're flipping a dime. Each one of them could be heads or tails, but we only have 2 coins. So how many ways can we get 3 heads if we're only flipping 2 coins? Well, if this seems strange, again, just go back to the sample space. We're looking for an outcome representative of 3 heads. Well, it looks like the maximum number of heads we can get is 2. We could get heads for both of the coins, but none of these particular outcomes represent getting 3 heads. So there's actually 0 ways to get 3 heads if we perform this experiment. So 0 ways to get the outcome we want, divided by the total number of elements in the sample space. We always have that same denominator. 0 divided by 4 is going to be 0. So this particular event has a probability of 0. That means it's impossible. There's no way we can get 3 heads running this experiment as described. So that 0 probability just indicates that this particular event is impossible in the context of our experiment. Okay, let's look at another example. Let's look at the dice sample space. So consider that 2 dice example. Assume the dice are fair and each roll is as likely as any other. Find the probabilities of the events that we previously defined. So let's go back and look at those. So event 1 was that a sum of 7 turns up. Okay, so we want to know what's the probability that we get a sum of 7 when we roll our 2 dice. Well, we started the same way as with the coins. We know what our sample space was, so we went and defined the sample space. Let's count how many things there are in the sample space, because remember, your probability has a denominator defined as the total number of elements in the sample space. Well, the individual elements are not individual rolls, they're combos of rolls. So each ordered pair, if we were going to write the combos as an ordered pair, each individual ordered pair is a single element of the sample space. So we have 6 different possibilities for the first die. We have 6 different possibilities for the second die. We actually talked about a counting principle that allows us to deal with a situation like this. If we want to perform a sequence of 2 actions, we determine how many ways there are to perform action 1, how many ways to perform action 2, and we multiply the total number of ways together. So 6 ways to roll 1 die, 6 ways to roll the other. 6 times 6 is going to be 36. So that means there's 36 elements in this sample space. There's 36 unique rolls if you think of one die as being different from the other. So that 36 is going to be the denominator for all our probabilities. That's determined based on the experiment and based on our sample space. So because the experiment and the sample space are the same, regardless of the event we're looking at, that number 36 is always going to be the denominator for the probabilities. What's going to change is what the numerator is. The numerator depends on the event. So event 1 is that we got a sum of 7. Well, how many ways are there to get a sum of 7? Well, we determined all of the elements that would be in that event, and there were 1, 2, 3, 4, 5, 6 different ways to get a sum of 7. So that means that the probability of getting a sum of 7 of event 1 occurring, there's 6 ways to get a sum of 7 divided by the 36 total different outcomes in our sample space. So our probability is going to be 6 over 36, which reduces to 1 over 6. If we convert that to a decimal, 1 divided by 6 is 0.167. Now, what if you struggle to reduce fractions, something like that? I don't have my graphing calculator here with me at the moment, but I'll talk you through how you would do this. If you were to divide 6 divided by 36, you would get the 0.167. But suppose you wanted the reduced fractional version instead. Well, start with the actual probability, which is just based on the definition of probability. Get your decimal. Once you have your decimal in your graphing calculator will take a decimal and it will convert it to a fraction if it's possible to take that decimal and convert it. Some decimals are irrational and they can't be converted, but otherwise they will be converted to a fraction. If you go to the math menu on your graphing calculator, which is on the left-hand side of the graphing calculator, and hit the math menu button, the first option is going to be arrow frac, which just says take your decimal, convert it to a fraction. So if you do the division and get your decimal, go and choose that arrow frac operation, and then that will convert this decimal to a fraction. And what you'll find is it's going to be the reduced version of the fraction. So if you get, for instance, a large fraction, this one may not be too bad, but suppose you had a really large numerator, a really large denominator, and you're not sure where to start reducing. Maybe they do reduce, maybe they don't. Do that division in your calculator and then take the decimal outcome and convert it to a fraction, and it'll reduce it for you. So that's a quick shortcut to take care of that kind of problem if reducing the fractions is something you struggle with. Okay, so back to the probability. What about event 2? Well, event 2 was that a sum of 11 turns up. Well, how many ways are there to roll in exactly an 11 as a sum? Well, we could roll a 6 and a 5. We could roll a 5 and a 6. So we have 2 outcomes representative of this event. So there's 2 ways to fulfill this event's requirements divided by the 36 total possibilities. So 2 out of 36 is going to be our probability, which reduces to 1 out of 18, or approximately 0.056. So notice that this is a smaller decimal than the one above. Having that 0 in the 10th place tells us that this is a smaller decimal than the one above. What that means is that the first event is more likely to occur than the second, because the probabilities differ in that way. So a higher probability just means the event is more likely. Now, event 3 was a sum less than 4. So in other words, rolling a 2 or rolling a 3. Well, there were 3 ways to get a sum that was less than 4. So 3 different outcomes represented in our event divided by the 36 total possibilities. So our probability is going to be 3 out of 36, or 1 out of 12, or approximately 0.083. And then the last event I remember was rolling a 12. Well, how many ways can we roll a 12? The only way to roll a 12 is to roll 2 6s. That can only happen in one way if you roll those 2 dice. So there's one way to get a roll of 12, a sum of 12, out of the 36 total possibilities. So this probability is going to be 1 out of 36, or approximately 0.028. So out of the 4 events, the last one is the least likely event. We can actually determine which is most and which is least likely just looking at those non-reduced fractions. So whichever one has the highest numerator is the most likely. Whichever one has the lowest numerator is the least likely. Why can we make that one-to-one comparison? Well, we can compare them because the denominators are all the same. So it's apples to apples. If the denominators are all the same, then what's changing the actual values for the probability is the numerator. A higher numerator means when we do the division, we still get a larger result. A lower numerator means when we do the division, we're going to get a smaller result. So that's going to allow us to compare. It also makes sense that rolling a 7 would be easier than rolling a 12, just because there's different ways to roll a 7, whereas there's only one way to roll a 12. Now let's look at a slightly more complicated example, maybe one where we can't really make a list of all the different outcomes in the sample space. Okay, So we're going to draw 5 cards from a full deck of cards without replacement, which means draw the 5 cards and draw them and don't put them back in the deck. So in other words, don't draw a card and then put it back 5 times. We're being dealt 5 cards, a hand of cards. What is the probability of getting 5 spades? Okay, so start by defining the experiment. Think of that as the actual physical action being taken. What are we actually doing physically in this problem as described? Well, we're dealing 5 cards. We're drawing 5 cards. So that's the experiment. Why does that matter? Well, that's going to help us define the sample space. The sample space is all the different outcomes we can get when we draw 5 cards. So the sample space is all the different 5 card hands you can get. It's not all the cards in the deck, it's all the different combinations you could get when you draw 5 cards. So maybe you could get all aces and then a king. You could get all aces and then a queen, all aces and then a jack. All of those would be considered elements within this sample space. But you'll find if you try to make a list of all the different elements, there's no way you're going to be able to do it. You're going to run out of time. You're not going to be able to do it because there's just too many events in this sample space. There's no way to make a list of all the different 5 card hands. I mean, technically speaking, yes, you could do it, but it would be so long and so tedious, there's really no point in doing it. But keep in mind, we don't have to know what do all the elements look like as long as we know conceptually what they look like. What we're really interested in is what is the size of the sample space. So remember, when we're talking about probability, we're comparing how many ways are there to get the outcome I'm interested in divided by how many total elements in the sample space. Well, as long as we know, generally speaking, what's in the sample space, we can determine how many elements there are in the sample space. So let's start by making that determination. So our sample space is all the different 5 card hands we could be dealt from our standard deck of cards. So the number of elements in the sample space is actually going to be 52 combination 5. So remember, we talked about permutations and combinations. A permutation is some draw, if you want to think of it as drawing cards, something like that. You're drawing without replacement. In other words, there's no repeats. Once you draw, you've drawn it, you can't use it again, but the order matters. The difference with a combination is we're drawing without replacement, but the order doesn't matter. We know with a hand of cards, the order we're dealt the cards in doesn't actually matter. You can rearrange the cards in your hand and it's still the same hand of cards. So that means it's a combination. Well, when we're talking about a combination, it's how many things do we have to choose from and how many out of that group are we choosing? Well, if we're choosing 5 cards out of a deck, we have 52 to choose from, and in this case, we're choosing 5 out of the group. So in terms of all 5 card hands, the sample space, all the different outcomes for this particular experiment of drawing 5 cards, it's going to be 52 combination 5. If you plug that into your calculator, remember that's under the math menu and then the probability submenu, that's going to come out to 2,598,960. Really, really big number. So this is the total number of different 5 card hands you could get. Keeping in mind, again, we're not worried about how the cards are arranged. So the same 5 cards just dealt in a different order is considered the same 5 card hand. But these are all the different combinations of 5 cards that you can get from your standard 52 card deck. So that is going to be the denominator of our probability. That's all the different possible outcomes we get in total from the experiment of drawing 5 cards. Now the event is the particular situation, the particular outcome we're interested in. So what we're interested in from this particular experiment of drawing 5 cards is the event where we get specifically 5 spades. Okay. So we need to define our event and we need to know how many ways are there to get that particular outcome. How many different elements are in that particular event, if we think of that event as a subset of the sample space. So our event is getting 5 spades. So how many elements are in this event? Well, how many different ways are there to get 5 spades? Well, keep in mind the only way to get 5 spades would be to make sure that we're drawing only from the group of spades. Well, how many spades are there in the deck? Well, there's 13. So we have 52 cards in the deck, 4 different suits, 13 cards per suit. If we just want spades, we have 13 spades to choose from, and out of that group, we're choosing 5 of them. So 13 combination 5 is going to be all the different combinations we could get where we have exactly 5 spades and no other cards of any other suit. 13 combination 5 comes out to 1,287. So there's 1,287 different 5-card hands where all the cards are spades. Once I have these two components, I have my probability. So the probability of getting 5 spades is going to be the number of ways I get the specific outcome I'm interested in, which is 5 spades in a hand of 5 cards. We know there's 1,287 ways to get 5 spades from a draw of 5 cards. And then the denominator is the total number of elements in the sample space. My sample space is all the 5-card hands, all the different outcomes I get from the experiment of drawing 5 cards, all the different total combinations. And we know that value comes out to 2,598,960. So that's going to be our denominator. So this fraction is our probability. Now, does that actually reduce? Remember, if you take this and divide it in your calculator, this will be roughly what you get. Keep in mind, you may get a number in scientific notation. If you get something that has an E next to it and then maybe a number, what that number is doing is it's telling you to move the decimal place. So if it's E with a negative number, it says move the decimal place that many places to the left and then fill in zeros as needed where you jumped a space and there was nothing there. If you wanted to see if this fraction reduces, remember, do the division and then math menu arrow frac, convert it to a fraction. If it just converts back to this, or if it doesn't convert at all, then you know you can't do anything with that fraction. Now, what I want to emphasize with this example versus the previous ones is notice with the previous ones, we actually physically defined the sample space. We went through and we actually determined all the different specific outcomes. That was not really a feasible option in this case. You can't really make a list of all the different 5-card hands you can get. Technically, yeah, you could do it, but notice we didn't actually need it in this case. All we had to do is determine what does the experiment look like. Based on that, what does the sample space look like? What does our event look like? And just based on what we know from a theoretical standpoint about a deck of cards, we can determine the 2 different components we need for probability just based on what we know about counting principles. So those counting principles, knowing the addition principle, knowing the multiplication principle, knowing how to calculate permutations and combinations, that's going to be used a lot for these kinds of problems because we can't make a list of all the outcomes for these kinds of problems. So going back to those counting principles, we're going to do that regularly. So always start by determining, are we looking at a combination where order doesn't matter? Are we looking at a permutation where order does matter? And then think about what the numerator versus the denominator of your probability looks like. Now let's look at another example that's similar to this that requires use of those counting principles. So the Board of Regents of a university is made up of 12 men and 16 women. If a committee of 6 is chosen at random, what is the probability that it will contain 3 men and 3 women? Now, start with the experiment. What are we actually doing? We're choosing a committee of 6 people at random. So choosing a committee of 6 people, that's the experiment, that's the action we're taking. So the sample space is all the different possible outcomes when we run that experiment, when we choose a 6-person committee. No restrictions. So when we talk about the sample space, it's tempting to start relating it to the actual event, to the outcome we're interested in. The sample space is run the experiment, no restrictions involved whatsoever. So if you were to take away the specific event in question and just look at that particular action you're taking, how many different outcomes can you get for that action with no restrictions involved? So the sample space is all the different 6-person committees. In other words, choose from the group of people without respect to whether or not they're men or women, just the group at large, choosing 6 people from that group. Well, does the order we choose those people in matter if we're choosing a committee? The answer is no. They can sit anywhere at the table and you rearrange them and they're still the same committee. We don't have a committee chair, we don't have anything like that. So this particular counting problem is going to be a combination problem. So again, we need to know how many items do we have to choose from, and then how many items are we choosing. Now, if we're just assigning a 6-person committee in general, no restrictions, well, we have 12 men and 16 women to choose from for a total of 28 people. So we're choosing from 28, and since we want a 6-person committee, we're choosing 6 out of that group. So 28 combination 6 is going to be the total count for 6-person committees. That comes out to 376,740. So this is the number of elements in the sample space. This is the total number of different committees we can form from a group of 28 people if we're choosing 6 out of that group. So that's going to be the denominator for our probability. Now, the event that we're interested in is a committee that has 3 men and 3 women. So we need to know how many ways are there to choose specifically a committee of 6 people, but specifically a committee that has 3 men and 3 women. We get a specific outcome, a specific subset of the sample space. Well, if we want to choose specifically men and women, specific numbers under each category, we have to do each of those choices separately. So we have to choose the 3 men out of the pool of men. We have to choose the 3 women out of the pool of women. Now, because this is a 2-step process, it's a sequence of steps, we count the number of ways we do step 1, we count the number of ways we do step 2, we want to do both of those steps, so we multiply together the number of ways to perform each step. So how about choosing the 3 men? Well, we have 12 to choose from, and we're choosing 3. Again, it's a combination problem because the order we choose them in doesn't matter. So we have 12 combination 3 for our choice of 3 men. We're also choosing 3 women. We're choosing them out of a group of 16. So that's going to be 16 combination 3. Each of these values is then multiplied together because we want to perform this 2-step process of choosing men and then choosing women, and we get a total of 123,200. So our probability is going to be 123,200, the number of ways we can choose that particular committee, the one that has 3 men and 3 women, divided by the total number of elements in the sample space. In this case, the total number of ways we can choose 6 people at random, no restrictions. And we determined that was 376,740. Now, as with the simpler problems, you do need to make sure that your fractions make sense. So remember, your numerator should be smaller than your denominator. If you do the counting components of your problem and you find that the count for your event is higher than the count for your sample space, then odds are it means you did the count incorrectly. Maybe you oversimplified or maybe you overcomplicated the count, something like that. But you should always have a smaller numerator than denominator so that when you divide, you get a decimal that's less than 1. So what does this mean? So 0.3, that means close to a third of the time, if you were to randomly choose a 6-person committee, you're going to get this particular combination. You're going to get a committee with 3 men and then 3 women. The rest of the time, you would get a committee that has some other combination. So maybe 2 men and 4 women, something like that. Okay. So those are just a few examples of theoretical probability. Again, notice sometimes we can look at the sample space specifically, sometimes we can define it in detail, or like in these 2 examples, we couldn't really make a list of all the different combinations, but we can count the number of combinations, and that's going to allow us to determine the probability. Theoretical probability, though, relies on the fact that choosing any one outcome versus another is equally likely. So for instance, for our 5-card hands, if the deck is fully shuffled, dealing any particular card is just as likely as dealing any other. One card is not more likely than the other if the deck is truly shuffled well and it's truly random draws. Same thing with choosing a committee. If you just throw people's name into a hat, all the slips are the same size, you're just as likely to draw anyone's name versus anyone else's. So the fact that it is, in a sense, random, it is hopefully truly random, is what allows us to use theoretical probability, the fact that all the outcomes are equally likely. Now, there is another type of probability that we call empirical probability. So empirical probability applies when we generate probabilities based on actual experiment trials. So in other words, rather than analyzing the experiment in general, we're analyzing it based on running the experiment and calculating data from the outcomes. So if we were to look at the same experiment from a theoretical standpoint versus an empirical standpoint, we may actually end up with different probabilities. So think of theoretical as like perfect case, perfect world. You ran the experiment if you were to do so, and you got, for instance, if you were rolling a die, there's 6 different outcomes. You got a 1 just as often as you got a 2, just as often as you got a 3, a 4, a 5, or a 6. In other words, perfect world, because every outcome is, at least in theory, equally likely, you get every outcome the same number of times. Now, you know, if you actually rolled a die over and over and over again, you may not get a 1 the same number of times, the same number as a 3, a 4, a 5, a 6, anything like that. It may differ in terms of the number of times. So empirical probability may differ. The accuracy of an empirical probability situation is going to depend more than anything on how many times you were to run the trial. So say you were to roll a die 10 times. Well, the probabilities you get from rolling 10 times, the data you get, would not be nearly as accurate and representative of the situation as if you were to roll the die, say, 1,000,000 times. If you were to roll it 1,000,000 times, more than likely your data will come out so that your probabilities are going to be closer to what's theoretical, in other words, best case, perfect world, than if you were to do it 10 times. But when we're talking about empirical probability, we're talking about actually performing the experiment. What are the outcomes that we get? And then basing our probability on actual trial data, actual outcomes, and not just a theoretical analysis. So when we want to determine an empirical probability, we're going to actually conduct our experiment. We're going to say n times. That's going to be an arbitrary number. Again, in real life, it could be any number we wanted, but for purposes of developing a formula, we're just going to call it n. So that's the number of times we're going to run the experiment. And we log how many times our particular event occurs. We're going to call that the frequency of the event, f of e. So if we run the trial 100 times and we're interested in an event E, how many times did we get that particular outcome out of the 100 trials? Based on those two values, the empirical probability of our event is going to be the frequency of that event, in other words, how many times we observed that outcome, divided by the total number of outcomes that we got. In other words, the total number of trials we ran. If we ran it 100 times, the denominator is 100. If we ran it 1,000 times, the denominator is 1,000. So how many times did you get the outcome in question divided by the total number of trials you ran? So let's look at an example. In 2015, there were approximately 254 million Americans ages 15 or older. The table below shows the distribution by marital status and gender of this population. Numbers in the table are expressed in millions. So columns represent marital status, and then rows represent binary gender, male and female. Notice the bottom row and then the far right column are totals. So totals across the row and then totals down each column. If you were to take all the subtotals and add them up, notice each sequence of subtotals adds up to 254 because there were 254 million Americans included in this particular table's data. So if one person is randomly selected from the population described, find each of the probabilities. Well, what's the probability that we get a person who is divorced? Well, how many times did we get someone who was divorced? What's the frequency of finding someone who is divorced from this table? Well, the total number of people who are divorced is going to be 26 or 26 million. So the frequency of getting someone who's divorced is going to be 26. Out of the total number of trials, or in this case, we can think of it as the total number of individuals represented in the table. Well, how many is that? Well, there's a total of 254 million in the table, so it's going to be out of 254. So 26 out of 254, which is approximately 0.102. Now, what's the probability that the person is female? Well, how many different ways are there to choose someone who's female? You can have someone who's female and married, female and never married, and then also divorced or widowed, for a total of 131. So out of the group, there's 131 ways to get someone who's female out of the 254 total in the group. So our probability is 131 out of 254, or approximately 0.516. So it's substantially more likely to pick someone who is female than it is to pick someone who is divorced, if we're not going to think about further categorizing them as male or female and divorced, female and married, female and never married, something like that. So keep in mind that these two events would be considered compound events. There's more than one way to get someone who's divorced. Think of it as male and divorced, female and divorced. There's different combinations. Female, we could have female and married, female never married, so on and so forth. What if we want to be a little bit more specific? So suppose the person has never been married and is male. So they fall into the category of people who are never married, and they also fall into the category of people who are male. Well, how many ways are there to get a person who's never been married and who is also male? You're looking for the intersection of those two rows and columns in this particular table. So never married and male intersect with a value of 43. So there's 43 million ways to pick someone who's never been married and is also male out of the 254 in the table, which is 0.169. And then the person is widowed and female. So they fall into the widowed category and the female category. So there's 11 people who fall under both of those categories. So 11 ways to get the outcome we want out of the 254 total, for approximately 0.043. So far and away, that is the least likely event out of the 4 described, just because that population is the smallest. It's going to be the hardest to randomly choose from that population. So that's just one other aspect of probability that we sometimes may encounter. In most cases, the idea of empirical probability is used to extrapolate data. So for instance, say you take a survey of 100 people around the area. Based on the values you see for them, based on the questions you ask, you can then make determinations about what you'd expect for the population at large. So in that case, that probability might be used to sort of make guesses about what you'd expect for a larger group, just based on the probability you saw from a smaller group. So we've looked a little bit about the fundamentals of probability in this video. We talked about an experiment, we talked about a sample space, and then we talked about that fundamental fraction defining probability. Keep that in the back of your mind while you're doing all your different probability problems. Having that definition handy is going to be really helpful, and it's going to help you determine where to start problems that otherwise may be a little bit more complicated.